say, considering the totality of the material, like there'd be like a loose port type evaluation, assuming some port, that port must flow and impacted the wall of the, closet, the reinforced fiber.
Impact of
Loose, well, we typically in nuke industry we consider loose port evaluation. Some piece
gravel,
it gets just caught the flow and impacts something. Yeah.
Okay.
They think nuts and bolts. In this case, we're talking about rocks.
Yeah.
Well, it would be like the smallest portion that could disadhere and then become a miscellaneous system. But treating that as kind of...
Or anything could be a missile. Anything from anywhere can be a missile. Actually, any type of potential port that could be in there.
It's a raw water system. What all can be in there?
Yeah.
Yeah. I mean, this is it has been used in penstocks and in steel mills and so.
We're not proposing that you have it figured out. We're just proposing please put it in.
Good questions to answer. Okay, so we have crack initiation, propagation, and impact from rocks and other things.
Well, and also potential failure of the carbon fiber process itself. What would be the largest acidification?
You're saying you have a problem if a sheet comes off and starts flying down your pipe before you
Your analysis. If it's so big that it can't possibly do something, those sort of things. But once again, I'm getting too much into the details, and we need to go.
Well, it's good to know to put it in the request.
Now, if I'm, when you mentioned delamination of the sheet, so that we consider that the sheet is delaminated, and then what happens with the rest of the system, or?
Yeah, so does that go into my pump? Does that cause me to lose suction? Does it cause me to have a failure of the safety function of the system? Those are the more the generic things, which I'm sure
is an approach to addressing that by doing preventive design and construction to minimize the likelihood of sheet failure.
That's up to you. One of the things that we have seen in linings and coatings of large diameter pipe is in certain circumstances rather dramatic delamination, and those wind up downstream someplace doing something bad. And so we have two things to consider. One, what is the effect on the piece of pipe where the lining now no longer is, and now you have potential for corrosion that you weren't planning on. The other one, of course, is if you wind up with a big piece of something in front of your heat exchanger, you have a problem. So someplace, some way along the line in your submittal, we will be looking for either what happens if this does happen or why can't it happen. Okay?
And you can talk about your strainer.
But in any case, that's something that we'll definitely be looking for because operating experience points us in that direction.
So even if these are not key phenomena, things that you would expect to see, at least say why they're not key phenomena.
It has to be addressed.
Right.
Okay.
That way it doesn't translate into an RAI that we spend 4 months resolving.
Okay. Other issues related to materials that are important so far as the entire system is considered is durability. So we have reviewed the available literature and the test results of this particular material to check that how it behaves with time in given environments. And the environments may be just regular water, then cold water, heat, and things like that. So these tests are considered as a part of qualification of material and will be provided. CFRP, just like any other material, has a distribution of mechanical properties when tested, and The slide here shows that it's tested by ASTM 3039, and that for design we use characteristic values of strength and modulus based on ASTM D7290. That would be 5th percentile with 80% confidence limit. So this would be for one layer of CFRP. Now, if in a typical layup you do not rely on one layer, but you have 2, 3, 5, or more layers of CFRP in one direction, and then for the properties, we do not just multiply the properties of one layer to get the properties of 5 layers. And the reason being is the distribution of properties then when you combine them, you can get a weak link, so to say, in one of those 5. So essentially the tensile properties of 5 layers are lower than properties of one layer multiplied by 5. So that's also considered in design of CFRP.
One comment, that you had on the previous slide, the minimum 50 tests, or minimum 50 samples. I know one thing that we've done when we've gone through the code case is we've talked about the basis for the number of samples that you've done of the testing. That basis included within, as you talked about a specific test or what you're doing, probably something we'd ask. So it would be useful to cite the reference. You have a number of them.
The basis for the number of required tests, yes. Then the next one is when we have the properties of the material, then the question is at which level of load can that material operate, and that's done by reducing the strength by some factors of safety. Now, I mentioned earlier that this Water Research Foundation project included testing, and it also included a substantial reliability analysis of materials and installations. And this graph on the lower right is taken from the WRF report. And for AWWA standard, which is load and resistance factor reliability based standard, this minimum reliability index is about 3. Now, in the case of the safety-related structures, we understand that the desired probability of failure is 10 to the minus 6 per calendar year, and that's based on the NEI document. And with the reliability index of 3.9, the minimum required factor of safety ends up being 2.15. Now, in practice, we're taking this factor of safety to be considerably higher. So for the hoop tension load, this minimum factor of safety that we'd consider would be conservative, would be at least 4. Which brings us to some of the basic approaches to design. We design circumferential and longitudinal directions independently, and we're using unidirectional fabric in circumferential and longitudinal direction, and comparable to the minimum wall thickness in the case of the CFRP, since we're working with the layers of fabric of some nominal thickness, we have the minimum number of layers that is required for the hoop tension and for longitudinal forces as well. So it would be calculated like this. Now, we consider all loads that can act at the same time, and consider both long-term and short-term loads, because CFRP is a polymeric material, and unlike steel, it's subject to creep, and there has to be a knockdown factor for long-term loads. So that's all considered in the design. And we consider the combined stresses, meaning that stresses from internal pressure, superimposed with the stresses from external loads. So, for example, if a pipe is installed in soil and it's being subject to bending and deflection from soil, the stress from that bending is superimposed to the stress from pressure to come up with and to check essentially the maximum stress is less than the allowable stress. In this particular case at Surry, we have a condition in which the pipe is encased in concrete, so there really is no bending loads acting on the pipe, so the stresses and the loads acting on the pipe are considerably simpler, and we would essentially check that the demand is less than the strength provided. I mentioned that buckling is a very important consideration, and for buckling, again, we check that all the loads that can act at the same time are appropriately counted for, and that they are less than the critical buckling pressure. So in this case, in the first case, we do not have the earth load, we do not have the surcharge load, we do not have live loads acting on the pipe because it's encased in concrete, but we considered a hypothetical case in which groundwater may be acting on that encased pipe and may be acting on the CFRP, and therefore that's the load that potentially can lead to buckling. And we consider a combination of vacuum, internal negative pressure, and groundwater also in evaluating buckling of the pipe. We use a similar approach with the appropriate loads, obviously, for longitudinal stresses, and given the short time of presentation, I did not put in the slides for it, but I think that we've discussed one aspect of it already. An example of how a design would look like is shown in this table here, taken from one of the drawings. So, for example, we have a 96-inch circulating water discharge pipe. We have the materials that are used, and eventually we have a layup. And that layup in this particular case includes one layer of the electric barrier, which is a glass fabric. Then we have two hoop layers of carbon fabric, one longitudinal layer of carbon fabric, and we have one water tightness layer, which is another layer of glass fabric, and then we finish it off with two hoop layers of carbon fabric. So this is all constructed sequentially, one after the other, and Anna will be talking about how it is monitored and inspected during construction to make sure that all goes as designed and appropriately. So some of the typical details on the drawings that are shown is, for example, the hoop section of the pipe that shows the minimum overlap length. It's like a development length for reinforcing bar. We have to establish the hoop continuity. Similarly, for longitudinal fabric, we also have to have an overlap length to establish longitudinal continuity of fabric, because you would not be building 100 feet of pipe at the same time. They may build 20 feet, and then tomorrow they can come and build the next 20 and so forth. So there's got to be an overlap to make sure that there is appropriate bond to provide longitudinal continuity. Yes, Joe?
It's interesting.
Okay. So there was a question earlier about some details, because in this case we have outlets, we have elbows, and so forth. So each of these details is specified by essentially specifying the layup in the main pipe and the layup in the outlet or branch line, and then tying it all together. So you can see, for example, on the left-hand side, it goes from 2.1 to 2.13, or 2.15. So there's 15 different layers and orientations of carbon carbon and glass fabric that are specified to go around this outlet to provide for continuity within the outlet.
Adhesion and then the areas in which you do NDE on these.
Yeah, so in this case, you can see at the end we have a whole free zone 6-inch minimum. So this would be the end termination. And that's where initially the UT is done to make sure that there is appropriate minimum wall thickness and that's where we consider that CFRP transitions into the steel portion of the pipe there. And incidentally, this one also shows that we have, in the termination regions, we also include a stainless steel expansion ring. So while we rely on the bond as belt and suspenders, we put the stainless steel expansion ring to press the CFRP in termination regions. But we do not count on it numerically to say that that's responsible for taking any load. We put it there just in case.
And Lars just wanted to make sure we mentioned on the slide that this is not to scale.
And I forgot to mention, this is far from scale.
This is not a gun barrel?
That can be maybe an inch or so thick.
So next we're going to go through the installation-related details. So talk through what's involved with the installation process, and then some of the different checks that are done along the way. Each one of the stages within this process have detailed procedures and protocols that document along this way. And one of the things that we'll get into later on is that within the last several Surry projects, each one of them has been treated as as dry runs as we head towards the applications that are proposed for the safety-related pipelines, so that we're constantly working on refining our procedures and protocols and adjusting things to come closer and closer to what would be necessary. As part of the pre-installation requirements, so before we ever begin the work, some of the things that are done as part of the project would be to go in and identify and verify all of the repair areas, have this be identified and documented by each of the major players within the equation, the installer, the third-party inspector, and the owner. They're also verifying that the materials are in the appropriate controlled storage and have the necessary environmental controls to maintain the temperature requirements for the materials. We're also verifying that the materials have the appropriate lot numbers, the appropriate expiration dates, and all those aspects up front. And then we're also, one of the questions came up earlier about environmental controls. You can see here's a sample of some of the types of environmental control equipment that would often show up on a job site. And Jason, from our operations side, could you convey to us a little bit more of what type of environmental equipment this is?
So this is a dehumidifier pumping in about 5,000 CFM. So it also has an inline heater. We're able to control the ambient temperature, which dries the air, and then we also have the heater, which is an inline heater to force cure and control the temperature based on the specifics that we need.
And I know we've had these discussions during the cookies, but as far as the differences between metal stamping and the quality controls that you have for the material coming in, we're probably going to need that section as far as the information for quality control.
Absolutely. So in terms of the major installation steps that are key milestones within the CFRP installation process, and each one of these has the associated procedures and QA/QC checks. That includes initial surface preparation of the material of the substrate, saturation of the dry FRP fabric using the mechanical saturators on the right-hand side, doing an initial primer on the pipeline after the pipeline has been cleaned, dried, and the surface has been prepared. Then installation of the GFRP and CFRP layers, build up the dielectric barrier, the structural reinforcement, the water tightness layer, as well as top coat. And then, as part of the installation of the CFRP, making sure that the fabric is aligned, there's the appropriate overlaps, that we've documented the environmental conditions throughout. And if there are any defects or anomalies identified. For example, if a layer of carbon fiber has a small air pocket that it formed, we're identifying that in process and remediating in process as part of the repair procedures and protocols. And then we're documenting the cure process throughout as well. So I mentioned earlier how there were Surry-specific project-specific procedures that have been developed, and so here shows just a sample of some of those procedures that we have been working on and refining each outage so far on the non-safety-related pipeline, and are used as part of the basis that would be for inclusion within the safety-related applications. Those include overall quality plans, project-specific QA/QC forms for each area within the pipeline, installation procedures, the CFRP installation, as well as service preparation and the termination ring installation.
Well, it wouldn't be something that we would necessarily be reviewing for their own sake as part of the review process. Would it be possible that you guys could make this available on all those server things where we can go and
Like an e-room? Yeah, I think we could do that. Yeah.
I think that would help us understand.
Sure.
Absolutely. So in terms of the different types of inspections and tests that will be done as part of the process, that includes visual inspections throughout each stage of the installation, from prior to installation, during installation, and post-installation. And during the NRC site visit, you were able to see some of the different steps and stages that were observed throughout that process. We'd be calibrating the equipment, such as the mechanical saturator equipment, doing daily as well as throughout to verify the right amount of epoxies being added into the fabrics. We'll be verifying the surface preparation up front, as well as doing fusion tests, UT readings to be able to verify at different locations. Doing an adhesion test to verify the bonds. Be making tensile test panels to be able to verify the material properties that were used in the design. And then documenting environmental conditions to verify for cure as well. And each of these would have acceptance criteria and qualifications for the personnel and records to protect for posterity.
Our discussions about those qualifications, those testing, and the e-requirement, are they going to be part of your submittal?
Yes, absolutely. So as part of this, there would be a qualifications and testing section that would be included. But here you can see just a sample type of form that would be used on these types of projects. So you can see for this particular form, what we're talking about is for an individual pipe region, and it's made too small for you to actually see all of the language. We're not expecting you to read it per se, but the concept here, you can see at the very top left-hand corner of that form, there is a pipe number. You can see in a little yellow, and this is for a particular pipe. This is almost like a passport that provides for every layer that was installed. See in that middle. Each layer that was installed, the environmental conditions when it was installed, different verification that was done throughout, and then in addition to verifying the materials, the temperature, environmental controls, we're verifying things like the overlaps that is per the drawing details.
We love our forms. Will this form be by pipe segment? Is that just the areas of overlap, or is that going to be considered the whole piping?
So what we've done for previous projects, the major thing is it needs to be something that is able to accomplish the level of quality that's necessary.
How about just a discussion about that point?
Absolutely. So the short answer is, for example, for a pre-stressed concrete pipe, it would be individual pipe segments. Because this is a metallic pipeline and we're talking long lengths and sometimes complex geometries, it would be broken up into smaller regions, and so we'd make sure to document what's being captured on a certain form, especially when it comes to the complex detailing, so that we can ensure that everything is being done in accordance with the drawings. And I think that would be something else we could provide, the sample of what we've done in the past, so you can see some of those. In terms of some of the key installation steps, you can see here we have procedures. We already mentioned before, the materials come in pre-measured part A and part B buckets. So there's no on-site having to figure out a little bit of this, a little bit of that. Mix all of one bucket with the other bucket, and then make sure that it's been thoroughly mixed. And then after verifying that it's the appropriate consistency, mixed for the appropriate time frame, that would then be used as a mechanical saturator to saturate the fabric. We would be doing the weight ratio test, which is weighing a piece of fabric dry on the scale, running it through the saturator, weighing it again wet, calibrating the gap is appropriate for the materials, and then documenting that information within our forms. We would also be, for the surface preparation, looking at both documentation of the profile, doing an adhesion test to verify the bond to the substrate, doing UT measurements near the terminal ends to verify we have sufficient seal at those regions, and then also verifying that the chloride content. So since it's a raw water line, on previous projects we have not had an issue with chloride, but potentially if you have a salt water line, that could be an issue. We verify to check that to make sure. And we have contingency measures in place to accommodate as needed.
You folks are a little bit brackish.
But the levels were quite low. It's something that's part of the procedures and protocols. As you notice, we have the materials on site as needed to make sure that it's accommodated. But we probably not govern the installation process for this project.
For the adhesion tests, how many do you essentially do, and then what triggers a new adhesion test to be necessary to be done?
We would make sure to have that included within the documentation, and so that's something, making sure that it's appropriately representative. So, and what that means exactly would be spelled out.
Okay. In the infield, though, you don't expect to be going into the pipe and cleaning it out and then making adhesion tests based upon what you're finding in there? This would all be mock-up type like.
No,
This is in the pipe. So this picture you see right here was done inside the pipe right prior to the installation.
Okay.
So the whole pipe is prepared, an area that's considered representative would be designated, and then that region would have a layer of glass put down and typically 1 or 2 layers of carbon fiber composites, and then do an adhesion test to verify that the bond is considered appropriate for what's necessary for that project. But we're not just doing an above ground mock-up and call it a day.
And that's the clarification. That helps. It's helpful.
Exactly. So we've also done and will have documented above ground mock-ups to show upfront design approach, and then in field we are doing these tests as well. And so that's an important differentiation.
What is the ambient temperature on the pipe?
Skip ahead one slide. So here you can see for the last project that was done for Surry, the top 2 lines represent the temperature, the other ones represent other areas of the pipe. So you can see the temperature was between 80 and 100 within the installation. Typically we keep the temperature above 70 just to make it so that there's a wide range in which the materials can be used. Because it's outage-related work. Because it's outage-related work, the materials can cure under ambient conditions. However, as Roscoe mentioned, within the time temperature cure profiles, the more that the temperature is elevated, the faster the materials cure. So because schedule is a component, we will often elevate the temperatures to be able to help accelerate the cure, even though there's a range in which would be considered appropriate for the application.
Usually underground, depending how deep the ground is, it's going to be pretty cold, like 50 degrees or something like that.
Correct. That's
What's involved?
Yeah, we have environmental control, so we actually use that whole air. Right. So it's going to be very quick to heat the air in that, but the metal pipe itself will take longer to get to that temperature. So once you put the first layer or so, that air is not, it's going to be insulating the pipe, so the pipe is going to try to get back to its ambient.
So we take air temperature as well as surface temperature measurements throughout the process, and the materials are curing throughout. So especially when on the inside air temperature, when we're talking 80 to 100 degrees for air temperature, the first layer may have had many more days than the last layer to cure because you're putting subsequent layers within the pipeline. And so the concern is not so much about that first layer going on because we're constantly keeping the temperature to allow for the heat to permeate. It's more of making sure that the very last layer that's installed has the appropriate time and temperature to document cure. And in addition to that, in addition to documenting the times, the temperatures that are provided in terms of curing conditions. We'll also be doing project-specific cure tests. So as Roscoe mentioned earlier, there's a degree of cure testing that can be performed where we have a small sample of the epoxy that can be sent off to a lab and verify that it has achieved the appropriate level of cure. And that would be done on a project basis, not just we've done a cure test, we show that it's good. This is used as a
verification testing of the installed epoxy. Essentially, they take a sample, which is a nail-sized sample, and send it for testing to verify that it has reached adequate cure.
Jason, you're controlling temperature from day one.
Yes, and we're monitoring 24/7.
And humidity.
Correct.
The air temperature you get started. Even as they're less, that temperature is recorded, and the final cure is beyond that, so that they're making sure that they actually plan for that material for that system.
And then from a success path standpoint, you can see here we've done comparable applications in essentially the very, very similar location, just a couple feet away from where the safety-related projects were. In the CFRP, we talked about this previously, but as you can see, we'll be verifying alignments, development length, and overlaps. From a qualifications and testing standpoint, one of the enclosures would include documentation on our qualifications and testing procedures and protocols, which would include within our qualifications process, we have the learning objectives, trainings, knowledge tests, and performance tests that would be associated for installers, installer supervisors, and their third-party inspectors. From an OE standpoint, one of the enclosures that we would include would document both successful OE within the industry. You can see a representative sample of some of the nuclear projects that have been done within the industry using carbon fiber for internal repair of non-safety related pipelines that were successfully performed. We would also be documenting some of the failures that have occurred within the industry. As we mentioned previously, the alternative request team has not had any failures. However, the failures that were done by others, we have been involved in some of the failure investigations and remedial work associated with removal of failed systems. And so we had experience on what went wrong and how we've gone to make sure that we've mitigated these issues. This is a specialty process. It's very important that as the NRC is reviewing this, it's not something that one can generically say, carbon fiber is great, go ahead and apply it wherever, whenever, by whoever. This has to be done by qualified technicians using qualified materials, using a qualified and conservative design, installation path, and procedures and protocols. Each one of those steps are necessary to have a clear path toward success. And the project team here has substantial successful previous performance and a clear path toward success. Here shows some of the different concerns and failures that have occurred in the industry and what mitigating actions that we're doing to help accommodate that.
How much detail do you guys plan on providing on this as far as for your submittal, or do you have a good reference that has all of this contained within it that would be able to use?
So one of the things is a lot of this information is, we'd say, sensitive, to say the least. Usually owners, particularly